Hey everybody, welcome to this talk entitled A Truly Technical Introduction to Apache Druid. My name is Peter Marshall. I'm Director of Developer Relations here at Imply, and there's my contact details. If you want to say hi, go to petermarshall.io and say hello to me. So in this talk, I want to give you information about what Druid is if you don't know, but if you do know what it is, maybe you want to share this talk with some other people so that they can understand technically what Druid actually is. Okay, so a bit of a backstory. Now, this is my memory of the backstory, but essentially it kind of went like this. So I joined Imply actually in 2018, but it'd been running for many years before that. Druid was open sourced in 2012. Remember, we kind of just about had Kafka. We had a big yellow elephant that would eat SQL and spit out results, which was quite nice. Really, to be fair, think that we probably were still learning how to build these proper architectures. And one of the companies that was trying to build this new architecture was a startup in San Francisco, and they were hoping to build a really cool consumer-facing user interface based on a lot of advertising data. So they tried lots of different architectural solutions for that. I took away that they had latency almost everywhere. They would try and do some kind of computation for a lovely little visual on this UI and it would crash. Or it was trying to contain real-time data, which was a fascinating new concept. That real-time data had to go into some kind of compute engine and then spend ages being processed before you could actually query it. So latency everywhere. That's basically the story that I got. And that team that includes people like FJ and Gian and Vad and Eric and the rest of the project got together and decided, well, let's go and build. It's a high-performance real-time analytics database. What does it actually do? Okay, so it breaks up data into time periods and clusters that data by dimension values. It columnarizes that data, it optionally localizes it to the query processes, it indexes it, it compresses it, and then the architecture allows for all of that data to be processed in parallel, a massively parallelized way. Now, I want to show you a screenshot of a very powerful and lovely, beautiful UI built on the top of Apache Druid. And this is what we call Pivot at Imply. Now, I show this just because it's a really good example of a user interface really taking the advantage of Druid. And there's lots of examples in the wild, right? Just go and have a look, but they all have similar characteristics. So, for example, on the left-hand side of the screen here, you can see that we've got all the dimensions from the table. There's a little pull down here, which has got the aggregates, the sums, mins, maxes, group bys. Now, in worlds gone by, I would have probably said, well, what we need to do here to build this, obviously, is to pre-compute all the possible permutations of all group bys and all dimensions. What it is instead with this UI is it's actually just using the power of a very fast group by engine, and it is executing the query every time someone does something with the expectation that the database will respond in sub-second periods of time. And that's very important because for the UI, it means that we can do some really cool things, like people can just go and edit the dimensions when they fancy, or they can change, they can have a 98th percentile, or they could have a count distinct operation, and the UI will remain responsive. That level of flexibility in filtering, in calculations, the kinds of visuals you can draw. If anybody's ever heard Vadim speak, he says, look mum, no apply button. What we're not doing is designing a dashboard or a visual and then saving it and then waiting for it to eventually be generated. What we're doing here is designing it interactively. So they're very ad hoc. Over on the right hand side here of this visual, what you can't really tell in this kind of wonderful GIF of a demo that I have, is that this data is real time. So we're not just talking about data that's maybe a day old or a week old. We're talking about stuff that's happening right now. Real time data alongside the historical data. You can read a lot more about this backstory by looking at the white paper on the Druid website, but also do go and sign up for the Tales at Scale podcast. One of the very first interviews is with Eric Cheddar, who, if I'm not mistaken, committed the very first line of code into the official Apache repo. Anyway, and of course, if you want to get going with any of these things, please do go and have a look at Imply Polaris. It's Imply's SaaS offering. Another thing that's very close to my heart is this Learn Druid repo. It's in the Imply data organization on GitHub. There is a learning environment You can spin up a ton of Docker containers, and then you also get access to Jupyter Labs, which gives you a whole load of Python notebooks you can go and play with. Let's get to the diagrams. Apache Druid consumes in two modes, either in batch mode or in streaming mode, and it consumes from either Kafka or Kinesis, any Kafka-like API. When it comes to batch ingestion, it's from object stores. We can also issue queries to Postgres and MySQL by using Druid. You can also bring in from HTTP and local files. In fact, if you do the quick start, you'll see that a lot of the examples come in over HTTP. Now, it is important to realize that Druid is the last data source before the user interface. It's the last thing that people will see. So I like to say that if you've got your data in Druid, it needs to be statistically ready. It needs to be ready for end users. So things like data cleansing or sessionization or enrichment of the data using some kind of ML model, very often in architectures of Druid that happens upstream. When it comes to UIs, Druid has two APIs. We've got the JDBC API, which is powered by Avatica, and then we have the SQL API, which operates in two different modes, synchronous and asynchronous, for the fast queries, or for slower queries powered by MSQ. So basically, any tool that supports any of those things can connect to Druid. Now let's get to the technical bit. Now I have three things because I'm an old enterprise architect. I like to put things into boxes and draw diagrams that no one looks at. But I like to think of Druid, especially when I'm comparing it to other databases, in terms of these three boxes: the architecture, the way it treats its data, and how it does its parallelism. So let's dig into the architecture. So this is a lovely screenshot of the Druid console. This is the services tab. What do you see? You see the coordinator, overlord, router, broker, historical, and middle manager. So these are the Java processes that make a Druid cluster. So starting with the router, which is that lovely lilac bar there. The router is like a central point for all of the APIs that you might want to call with Druid. Let's move down a layer to the broker. So the broker is like the gopher for all SQL. It decides where the SQL should be executed. So if you take a SQL insert statement, that goes down one route to the overlord, and that manages and controls the job of pulling in the data into the database. But if you take like a SQL select statement that you want to run really, really quickly, then that work actually is fanned out through the historicals route at the top there. The resource allocation, like where work actually gets done, is all dynamic. So ingestion and query are considered to be pooled activities. So the broker knows the state of the cluster. It knows what resources you've got available. So you can scale up and out. You can react to ebbs and flows in your incoming data. You can pump up your resources when you've, say, got a big backfill ingestion that you need to do, or if you need to reshape your data, take some dimensions out, clean bits up. You can pump up resources just for that. You can add more processing capacity just for the incoming queries. Also, we can add a lot of replication of services in here. So we can replicate processes that to do with planning and control activity. You can build a really nice high availability database. Okay, so that is the architecture. Let's now move on to the data and talk about how the data gets into Druid, what it's like, and how it's used at query time. So this is a typical insert statement. In fact, this is just one of the examples in the Druid console of the nested koalas to the max data. And can I say, if you've never been to the koalas to the max website, you are missing out. You need to go and have a look. So this is a typical insert statement. We specify where the source data is. And we then have to have a timestamp. It's designed for event data. It's event data analytics. So every row in a Druid table has a timestamp. Then we have all our dimensions. So that's all the measures and attributes that really enrich the user's experience. So we've got strings, and we might apply secondary indexes to that. We've got numerical data, we've got expressions, because we can do transformations in here as well. At the bottom here are two very important clauses. We've got the partition by clause and we've got the clustered by clause. And the partition by clause is saying when you get the raw data in, I want you to split it up into days. And the clustered by clause is splitting it up into another one of the dimensions, only one here in this example, but bringing it in so it's split up by browser. We'll talk about that a little bit more in a moment. What you can also do at ingestion time, because it's SQL, is do a group by. We actually call that roll-up. So you can front load your aggregate calculations. You can see here there's also this feature DSHLL in there. What that's doing is it's building an Apache data sketch of the client IP addresses. Those are very important if you've got very large scales of data and you want to do count distinct or set operations with theta sketches or quantile computations. Group by this roll-up process is really significant for you if you've got large volumes of data coming in, and actually users don't need that resolution. They probably don't have enough pixels for it anyway. How does this actually look on a cluster? So we run an insert statement, data is brought in from the source system, it's pushed into one of the dependencies for Druid called the deep store. This is an object store. This is a very conscious design decision in Druid because something like S3 or GCS or Azure Blob Storage, they are meant for very big scale data storage and for very huge numbers of parallel operations pushing and pulling data. You can do encryption of them. You've got resilience built into them. Now the data, when it's put in, is put into an optimized data format. They're like the base unit of work for all queries. So these are pushed into the deep storage area frequently. So with streaming ingestion, this is done in an ongoing process. There's a very detailed technical presentation from Sergio Ferragut in my team if you want to know how that works in detail. With batches, the pushes are done at the end of the batch. And in the Druid console, you can actually see this. So you can go to the segments view and you'll see all of the files. Now, what's important about this segment format? Well, it's columnarized, number one. That means when a query runs, it's only going to look at the fields that it needs to when it's doing aggregate operations. They also have dictionary encoding, they have bitmap indexing. Those two things are very important for binary operations, for filtering, and also for not storing a ton of data that you don't need to. You can hear a lot more about that. There's a brilliant talk by Gian at Carnegie Mellon University who goes into the detail of that. But you can also read, of course, in the documentation. So these ingestion tasks, they produce a segment about every 3 to 5 million rows, but remember that partitioned by clause, remember that clustered by clause. What Druid's really doing is it's generating a timeline of data. So when you put these segments end to end, you end up with a timeline. So your table over time is split up into chunks. It's also split up according to dimension values if you want to. You don't have to do that. So this means that filtering operations based on time, or those clustered dimension values, or if you're comparing them, is much quicker because you only need to go and look at the specific bit of data that contains that time period or contains those cluster values. It also improves group by operations as well. So you can see that in the segments view. You can see the start and end timestamp and also which range of dimension values each segment file covers. Now these segment files are immutable. They're immutable because we can do lots of caching up and down the execution workflow. And in Druid we have versioning on top of that to enable lifecycle management. So the schema is actually stored inside these segment files as well. And that's how you get schema evolution. It can be weird when you start to use Druid and there is no create table statement. You're like, how do I create a table? Well, actually, the table schema is realized out of these segment files. The advantage there is that if you want to change your source data schema, yeah, fine. You can turn on auto schema detection. It brings the thing in, and over time your schema can evolve. Okay, so that's the data in Druid. It is this very optimized data format, and it's one of the building blocks of Druid. It's a really important reason why Druid gets very fast query response times. The other reason is the parallelism. Parallelism is everywhere in Druid. So let's talk first of all about ingestion. So when you give Druid your input source, it can split it up, and it splits up the work, parallelizes it, and then parallelize pushes that into deep storage as well. So parallel in, parallel push. So for example, with Kafka, it's splitting it up according to partitions in the topic. Since I'm talking about Kafka, I should mention that there is a very careful process in Druid called handoff. If you're a Kafka user, you're thinking about using Druid, make sure you go and familiarize yourself with that. Basically, it's about exactly once semantics in Druid. But the story here is parallel ingestion, parallel push into the deep storage. Now, because of that dynamic resource allocation thing we're talking about in the architecture, it does mean it's very easy to scale the ingestion resources up and to increase the parallelism, or if you want to do more jobs, just by adding more of the middle manager processes. We can also replicate the work that's going on within these processes as well. So you can have multiple workers consumers, if you like, pulling in from the stream at the same time, for example, to increase parallelism and resilience. So remember this lane I was talking about, which is very much dedicated for these sub-second query response times. When we want to use that lane, we pre-fetch that data onto those query processes. It gets put onto the local disk. The thing that makes sure that happens is the only process I haven't talked about so far, if you remember that screenshot, and that's the coordinator. The coordinator is there to do data distribution, it's there to do data management, and that data distribution thing includes pre-populating the historical processes with copies of the data from the deep storage. It reduces latency even further. So this data distribution thing, remembering this dynamic work allocation thing, it means that you can add and remove historical processes and just add them when you want them and take them away again afterwards, and the coordinator will make sure that data is distributed well and that it's balanced well over time. Now I'm talking about parallelism here. Inside the historical processes, each segment is processed by a single thread inside the historical processes. And if you've got more than 2 or 3 or 5 or 1400 historical processes, that query execution is parallelized across the processes as well as inside the processes. But not all query patterns are the same, and not all SLAs that we have for query response times are the same. Maybe we want to split off that work to a different area of the database. So in Druid, that is called tiering. So maybe the original node that we had there has got loads of CPUs, loads of memory, maybe not a lot of disk, but it's there to answer queries as quickly as possible. And then we'll have other processes on different nodes that maybe have fewer CPUs and less memory, but they might have a ton of storage. Now the coordinator kicks in here. It's this thing that automatically effectively moves the data onto the appropriate tiers. So a very common use case for this is if you have a table and you've got a year's worth of data in it, maybe everything older than 9 months, you're going to put that onto a ton of infrastructure which doesn't have as much power, because people aren't going to be that interested in response times on that older data. There's a few other little magic tricks that go on here with regards to performance, and one of those is that inside these historical processes, it uses operating system level memory mapping. So instead of reading from disk all the time, if there are segment files that people are looking at a lot, they're likely to be in memory until they're evicted, but it just reduces the expensive disk read operations. In the best case scenario, if someone is constantly hitting the same segment files, so that's the same time period or the same dimension values, it should be in the memory mapped area, right? So you will end up with an in-memory parallelized query execution. Now, I've also talked a little bit, when I showed you that demo, I was like, oh, look, it includes the real-time data, and you'll be looking at this and going, yes, but it's got to go into the middle managers, then into the deep store, then be pushed into historicals, and then it's queryable. Well, actually, if you're using streaming ingestion, for example, it actually includes the data as it's being ingested on those middle manager tasks as well. It's just parallelizing across the historicals and across the middle managers tasks as well. And this kind of open up like things like periodic comparison. It is going to look at the specific periods of time as they are available on whichever processes they're available, and then parallelize the query, fan out, and then merge the results again afterwards. And also if you're comparing, like, well, okay, what's dimension filter X compared to the same dimension filtered Y. If you've clustered by that, that again could be going to 2 different segment files and executed in parallel. Okay, what else have I got to tell you? Well, let's talk about the slower lane. So we've talked about the fast lane with the prefetch and lots of parallelism. Isn't this brilliant? Excellent. We all want to use Druid. The alternative route is because of this MSQ engine, the multi-stage query engine. What does it do? Well, the clue is in the name. Instead of a fan-out, fan-in process, it's very much based around things being done in stages and those stages communicating with each other. And that route is definitely something you need to go and investigate if you have got select queries that run for a long time. The results of those, for example, end up in something called durable storage asynchronously. And it also, very recently, has also been given the capability of reading directly from deep storage. A few other things that Druid does as well, I really should mention before I finish. I've talked about caching already. There's multiple levels of caching inside Druid. from the broker all the way down. You can also prioritize your queries. I've seen this used in paid versions of UIs, for example, where if people are paying you money, you will prioritize those queries over other people. I've heard of other people using it just to make sure that their VP is happier by tagging all their queries as more important than everybody else's. But anyway, that's query laying and prioritization. And also approximation and vectorization. Now, approximation is another topic. If you don't know what an Apache data sketch is, it's time you did. It's an absolutely brilliant project. It's a fantastic piece of computer science. As I said, you can bring these in and generate them at ingestion time, but you can also make use of them just with the data you already have. So top n approximation, count distinct approximations, whether that's set operations or not, percentile calculations, so ranks, percentiles, all of that is powered by the approximation engine. Unfortunately, I don't have enough time to go on and on about approximation and data sketches today, but there's lots of other videos out there. Go and have a look at those. And of course, on the Learn Druid repo, we've got some notebooks you can play around with. So lots of other bits and pieces that happen in the cluster, all to make sure that this power is used in a very lean way, in a very proficient way, and in a very parallel way. So that's it, really. The things to remember are Druid has a shared nothing microservices architecture. So that gives us the resilience and the scalability options when we deploy Druid. It's that segment format, that columnar format with lots of compression going on. It's where those end up, whether you prefetch them or not, whether you employ tiering or not. And it's that asynchronous query engine for those long-running queries, as well as the really fast engine for those like sub-second queries. And then it's the amount of parallelism that happens in Druid, both on the ingestion side and the query side, and the flexibility that we have when we scope out our Druid deployments in having lots of ingestion resources, or not very much, or lots of query resources and not very much, because of that architecture. Okay. So that's how Apache Druid helps build people applications, because you can get sub-second response times, you can build it so that you can bring your streaming and historical data in, you've got this evolution of schemas over time, a very fast group by engine if you want one, you can deal with lots of different types of workloads, and the architecture gives us that ability to have scalability and robustness in what it is that we build. I hope that was interesting for everybody. And thank you very much for watching. Cheers.